All right, lecture 3, everybody. Let's get started. I have yet to update the attendance from Wednesday. It's just been a very hectic week, as I imagine it has been for some of you. I want to commend our student chapter for putting on another wonderful technical conference yesterday. Went off very well. I guess I'll also mention, I don't have it here on the announcement side, but I'll also mention that we have one of our prospective faculty candidates for our open environmental engineering position is going to be presenting today at 2. And so if you have the time to attend, that'd be really awesome. Homework 1.1 was due today. I sent a note about I had noticed a couple people were submitting the homeworks and they were getting the right answer, but they had put like foot tips, and so because it was a numerical field, Blackboard was getting angry and saying it was it's wrong, even though it wasn't. So so hopefully that email that I sent assuaged that. I think that this homework that I'm assigning today is going to be formatted in a similar way, but it's also going to have some like multiple choice questions. So the upside is I don't really think that's going to have too much of a there's not going to be too much of a problem from a data entry standpoint. And I'll go ahead and tell you now about that homework and then make a note on it. So the purpose of homework 1.2 is to force you to open this. This can seem a little daunting at first, and so I kind of just want you to get familiar with it. And so basically it's just going to be sort of a lookup homework where you're looking at values and inputting them. It's pretty straightforward. One thing I will mention though is I imagine, so I have the homework due on Wednesday, but I do imagine there's a possibility that some of you might be waiting for your assignment, or not waiting for your assignment, waiting for your manual, okay? So if it doesn't come in, I'm going to be pretty gentle on late penalties with this one, because I know you can't really do anything about it if you're waiting on UPS or something for the manual to arrive, okay? So, but I'll say do your best to try and get it done by Wednesday, but if not, if you're still waiting on the manual, it's not the end of the world. Fortunately, if your manual comes in, you should still be able to do this assignment because it's not a very long assignment. It's a pretty quick one. Okay, did everybody get the code? Everybody get the code? Okay, all right, so let me pull up our notes for today. So our topic today, I'm not sure what other professors who teach steel design across the country do. I know when I took this class, I don't think my professor had a day or at least a portion of a day devoted just to the manual. But we are going to be using the manual quite a bit, and I've found that if we just take some time and talk about the manual, it makes the coverage of later topics in the semester a lot more smooth instead of having to stop and go, oh, by the way, here's where you find this value. If you have a general understanding of how the manual is organized, then we can get through later topics a little bit more smoothly, okay? So just a little background. So AISC is the American Institute of Steel Construction, and basically what they do is they represent the steel fabrication industry here in the United States. They are the prime place where you're going to find any technical specifications relating to any type of fabricated structural steel product that you're going to use, period. Okay? And they publish and produce quite a bit. They produce design guides, specs, technical manuals, things like that. Obviously, one of the most popular publications they produce is the Steel Manual. I do want to mention that as students, you can, I think you had to create an AISC account in order to purchase the manual, right? Well, as now holders of AISC accounts, you are able to access design guides, for example, for free. And if you're a practicing engineer, those things are pretty pricey, so they gave them away. So I'm just saying, I think there's about 40 of them now, 40 design guides. And each one of those design guides, I think they're like $50 a piece, so you just got like $2,000 of literature for free. So just saying, it's pretty cool stuff. Okay, Let's talk about how the manual is structured, like sort of its anatomy. So if you look at the pages, okay, so what you're going to notice are these little sort of blockouts, and they'll say things like DIM or GEN or beam or column, tension member, whatnot. Those are different parts of the manual, different sections, if you will, okay? And there are like 17 different sections. But if you want me to sort of simplify that for you, I sort of think of the manual in 3 big chunks, okay? So the first chunk is what I'm going to call parts 1 and 2. That's just the dimensions and the material properties. In other words, like when you start doing your computations, you're going to need to know, okay, what is the flange width of a W10 by 49? What is the radius of gyration about the z-axis of an L6 by 4 by 1/2? You're going to need to look that stuff up. What is the ultimate tensile stress of A572 grade 50 steel? That's what parts 1 and 2 are for, are mainly for you to look up your reference values and your input values for the purposes of your calculation. So you're going to spend a lot of time in parts 1 and 2 throughout the semester, bless you. You're going to spend a lot of time there just looking up stuff, okay? I'm going to skip ahead to part 16. So part 16, bless you, starts where it says spec, S-P-E-C. That is the specification, okay? Now the specification, I'll talk about this in a little bit more detail later, but the specification is basically the rules that we're following when we design steel structures, okay? And that's where our design equations are and our specifications and so on and so forth, okay? Everything in the middle is sort of what you're paying for, okay? When you paid that, what, $125, that's what you were paying for, is the stuff in the middle. Because you can download part 16 for free, and you can, for example, the spreadsheet that contains all the dimensions of roll shapes, you can download that for free. This is what you're paying for, okay? And you can tell this section, if you start leaping through it, you'll see the, let's see, you'll see like the colored pages that look like this. That's when you know you're in the design guide region, okay? So that's what you're paying for, okay? So the first thing I want to point out is that, so let's talk about like the dimension part. So this is in part 1. So if you happen to have a steel manual with you, you can open the very beginning of the manual to a page like this. And if not, it's not the end of the world. I mean, you can just sort of follow along here on the screen. But for those of you that have your manual with you, where I'm at is sort of in this earlier part of the manual right here where you can see the rolled shapes. And again, I'll mention, when we start getting into steel design, you really are going to need to bring your manual with you every day, because we are going to be opening it every day to look up values. Okay, and I mean starting like next week. Okay. Excuse me. All right. So one thing I'll mention is that you do want to probably what I'll call tab various sections of the manual. So if you look at my manual, you'll see there's these like tabs right here, and there's these reference tabs. This is a really big book, and if you're in the middle of a celebration of learning and you need to quickly find a given sheet in the manual, it would be easy if it's bookmarked, okay? I will try and give you some guidance as to what I think is important to tab throughout the semester. What I'll tell you at least now is that, so I have a series of tabs at the very beginning for all of the rolled shapes. I don't tab every single section, but the ones that I tab are the W shapes, the C shapes, the angles, and the T's. Okay, those are the ones that I've tabbed. And I would say that 99% of any problem we're going to do in this class, that's more than enough. You don't need to tab like every, the double angles and the MCs and the HP sections. You don't really need to do that. The pages there aren't that many pages, so the more you use the manual, you'll see it's pretty easy to find stuff. There's a pretty logical order to how things are organized. Okay. So if we look at the, so let's actually focus a little bit on some of the data here. So let's say we're looking at one of these shapes. So the way that the manual is organized, so each row corresponds to a given rolled shape. So this would be the data for a W24 by 103, a W24 by 94, W24 by 84, etc. So if we're looking at the W24 by 62, so I've got a couple values here highlighted for that. But all of these values are the numerical dimensions and section properties associated with that shape. So, for example, if I have 18.2 right here, what is 18.2? Well, it's the area, right? So what is the cross-sectional area of a W24 by 62? It's 18.2 square inches. Where did I get square inches? Those are the units, okay? One of the things that we are going to start using in here is a very specific set of notation and terminology. One of the things that steel design is pretty good about is maintaining a consistent set of terminology. So, like, for example, if I use the term B sub F, okay, it has a very specific meaning, okay? That meaning is the flange width, okay? And so what I mean by that is if I have a rolled shape, like an I shape, I'm talking about this dimension. That's the dimension I'm talking about. Now, where am I getting that? I'm getting that from right here, okay? So if you look at each rolled section table, there is an associated schematic that will tell you what all of these values mean. So for example, what dimension is T sub W? Well, it's the thickness right here. It's the thickness of the web, okay? So it will tell you what that is. Now, one thing that's kind of interesting is that for some of these dimensions, there's two values. So for example, the flange width, we have 7.04, but then we also have 7. And then for the flange thickness, we have 0.59, but then we also have 9/16. What? Which one do we use? Okay. Well, let me explain what's going on here. So for any what I'll call measurable values, and by measurable values, I mean values that you could literally take a tape measure and measure in the field, okay? You're going to have two sets of quantities. You're going to have what's called a design dimension and a detailing dimension, okay? So this design dimension, you're going to know the design dimension because that's the one that's going to be in a decimal format. The detailing dimension is going to be fractional. The idea behind the detailing dimension is that if you're out in the field and you pull a tape, what is the nearest dimension that you're going to find to, say, a 1/16 of an inch? So, like, for example, if I have a W24 by 62 and it's out in the field and I pull a tape, it's going to probably read 23 3/4 of an inch. Even though for the purposes of design, I probably ought to use something a little bit smaller like 23.7, because 23.7 is the statistically calibrated value that's collected from measuring all of the W24 by 62s that we've produced over the past number of years, right? Okay, so what I'm getting at is this is a design exercise. We are talking about design, right? So between this and this, which value do we use? The design value, okay? So we use the decimal values. Don't use the fractional ones for your calculations, okay? I'm saying this, and I am telling you, there's somebody in this room who's going to do a homework assignment, and they're going to need the flange thickness, and they're going to put down 9/16. But I'm going to ask them to stick their hand out and do this. Because, nope. We use the decimal values, okay? Because the decimal values are those calibrated for the purposes of design. Everybody okay with that? All right. Okay. All right, so let's talk about the stuff that you're paying for. These are the design aids. So the design aids, you'll definitely be able to tell what you're looking at because they will be they'll be colored. Okay. Oh, I changed this image since the last time I taught this. So this is actually wrong. This is not for bolted connections. This is for beams. Whoops, that's definitely the beam, the ZX chart for beams. I think I used a different image since the manual got updated. AISC recently released a digital copy of this manual that I used for making the slides, and I think I changed this image because it was a little clearer from the last manual. Okay, so this is a very useful tool that we're going to use later in the semester. This is the ZX chart, so we're going to use this for designing beams. And you'll definitely be able to tell when you're in the design charts because they're colored. And specifically, you're going to see two colors, green and blue. Or if you have, color blindness and whatnot, one's shaded and one's not. And that's why they shade like that. So in this class, if you remember from the last lecture, we're not going to use ASD. We're going to use LRFD. So in this class, we use the blue numbers. We don't use the green ones. Okay? Now, here's something else that's noteworthy. If you open up the FE reference manual, okay, the reference manual that you get to use when you're taking the FE exam, open up, they actually have this table, the ZX charts. It's in the manual, but they don't have any of the green numbers, okay? You're only using blue numbers on the FE as well, okay? So this chart, like if you open up the steel manual, it looks different. It actually looks a little smaller, and the reason it looks a little smaller is they cut out all the columns related to the related to allowable strength design. And really, the only difference between the two, so like for example, if you have a value, let's call it a nominal moment capacity, you can either take that nominal capacity and multiply it by a resistance factor, or a nominal capacity and divide it by a factor of safety. In the manual, instead of the term factor of safety, they just use the Greek letter omega. So that's the notation here is ASD and LRFD. But again, we're not going to use the green numbers. We're only going to use the blue ones. Everybody good? Okay. Okay. So the code and the specification. So this is the part in the back. We are going to reference this quite a bit throughout the semester. So this is going to be our guiding principle for determining capacities and determining strengths and whatnot. So for example, if I have, let's say, a tension member, okay, and I say, well, how strong is that tension member? How much load can I put on that tension member until it fails, okay? Well, that depends on what limit state you're looking at. And so what this document will say is if you're looking at the limit state of, say, gross section yielding, this is how you compute your capacity. If you're looking at the limit state of net section fracture, here's your expression. If it's block shear rupture, here's your expression. And so where do we get those expressions? We get them from here. Now, a little bit about the anatomy of the specification. One of the things you might be curious about is that if you look at the section of the manual, you'll see that there's sort of these like white pages, and then there's these gray ones. See these gray ones right here? Okay, so the difference between those are what's called the code and the commentary. So the code is what we're going to be looking at most often, because the code is basically, here's the expression you need to follow. Here's the equation that you're going to use. The commentary is more about where that came from, why that expression is used, what was the background behind it. Now, I'll say this, as a younger engineer, I'll probably be candid in that I probably didn't use the commentary all that much, and I probably wouldn't expect a young, like fresh engineer to use the commentary that much, because once you understand how to do what you need to do, you can go to work. Okay? The commentary, I do think, becomes very, very valuable when this manual gets changed. I mean, this manual does get regularly updated, and so if you've been practicing for, I don't know, 10, 20 years, and there's a manual that comes out and there's an equation that's changed, you go, wait a minute, what happened? It used to look like this, now it looks like this. Why? Open the commentary. It'll probably tell you, hey, this is what it used to look like, and here's why it changed, and so on and so forth. Okay? So yeah, we'll probably look at it a little bit. We won't look at it in heavy, heavy detail. There are some references in the commentary that we are going to use, but we'll talk about that a little bit later. Okay. Any questions about the manual? Okay. All right. So I have two goals for today's lecture. The first is just the manual, but the second is I want to talk about steel. Okay, I just want to talk about structural steel. I am not going to belabor the process of producing structural steel. And I'll tell you, if I did, I honestly think one of the best resources is the segment on how it's made on producing structural steel. Has anybody ever seen how it's made? How it's made is like ASMR for engineers, you know what I mean? Just put on a playlist and, yeah, I mean, come on. Oh, that's how jelly beans are made. That's how they produce golf clubs. I never knew. But they have a video on how structural steel is produced, and it's really good. What I will say is that for the purposes of this class, the only thing that I think is worth mentioning is that in terms of construction steel is only a fraction of the bulk of steel that we produce in the United States. The vast majority of steel that we produce in the United States is for automotive applications. For construction, it's only a small percentage of that, about 10% or something like that. But of the construction steel that we produce these days, the vast majority of that steel is recycled. Okay, we're not really mining raw, iron and ore and coal and producing new steel. Really what we're doing is melting and reusing old steel, okay? We're taking scrap, melting it in an electric arc furnace, and then what we'll do is once it's molten, we'll draw a sample, check the chemistry, throw a couple, additive elements, maybe some nickel, maybe some vanadium in there just to make sure the chemistry's right, and then just produce it again. And so I think like 93% of the steel that we produce in the construction sector these days is recycled. So other than that, I think that you probably talked about the process in 321, so I really don't want to double, or repeat material that you've heard in another class, because that's what the other class is for. But I will say a couple things about structural steel that I think is relevant in here. So if you've had your, either Engineering 216 or CE 321, you've probably seen this, a stress strain curve for mild carbon steel, right? So this is a typical stress strain curve. You all know that steel, at least for its, beginning load application, sort of behaves like a rubber band, that it will behave elastically until you hit, yielding. If you keep your stresses below yielding, when you let it go, it snaps back to its original condition. Once you get past yielding, you start getting permanent deformations, right? One analogy that I heard a long time ago that I really like is that, so one of the advantages of structural steel is that steel is a material that is very ductile. If I asked you to describe ductility, do anybody have a good definition for that? When I say it's ductile, what do I mean? Was that talked about in 321? So what is ductility? All right. Like you're talking about, okay, well, what is it, Russ?
It's not brittle.
It's not brittle. Yeah, well, that's true. Yeah, that's true. It's the opposite.
Able to be bent to the shape.
Yeah. So okay. So that's a good answer. I'll give you an answer that extends that and relates it to this. Ductility is a material's ability to withstand deformations past yielding. Okay. And what to give you an analogy here, let's say that this line right here and this line right here are either ends of the end zone on a football field. Okay. So like touchdown over here, touchdown over here. Okay. All right. So here I'll put my little end zones right here. End zone, right? Field goal, right? Okay. All right. So if you want an analogy in terms of how ductile steel is, this line right there, that's about the 1 yard line. Okay. So all of the elastic behavior, which by the way, a lot of times we tend to try and keep steel's performance in the elastic range. A lot of times we're trying to keep the stresses between the end zone and the 1 yard line. So you get kind of idea what I mean in terms of ductility. Steel has a wonderful ability to withstand any elastic deformations. This part right here, where we start to begin strain hardening, where we start to get the steel starts, the structure start to realign and it can start taking load again. That's about the 10 yard line, okay? And then we can keep on going. When you're applying the load, the ultimate tensile stress, that's when the specimen starts to do the necking, when the center starts to suck in a little bit, and then it goes. All right? Does that make sense? Okay. All right. So there's a couple critical values that define the behavior of a stress strain curve. And when I say critical values, I mean values that we care about for the purposes of design. Okay? So really what we care about are this and this, okay? So we care about the point at which, we can consider it's behaving elastically or not, and the point which is the ultimate maximum tensile stress, which we call Fy and Fu respectively. The other two values that we care about are right here, the slope of that line, okay? And remember we have a name for the slope of that line. What do we call that? Well, that's Young's modulus, right? That's the ratio between stress and strain in the elastic range. And then we also care about the unit weight. Now, the thing about structural steel is that Young's modulus and its unit weight are not affected by the grade of steel, okay? There are varying different grades of steel that we can use for structural applications, and none of those grades have different Young's moduli or unit weights, okay? So the Young's modulus being 29,000 KSI for steel, and its unit weight being 490 pounds per cubic foot. Those are values you can set your watch by. Those are not going to change. What is going to change is FY and FU, and basically like the higher grade of steel, the different, the higher those values can be. Okay. Now, this is another table that I would tab in the manual. This is table 2.4. If you borrowed a manual from somebody, I bet that this table is already tabbed. Did you borrow this from somebody?
Yes.
Let's see. Hold on. I'm curious. I'm just curious if it's tabbed. Boom. It's tabbed. He called it steel types. Right there.
Thank you.
You're welcome. But I was just curious if that was the case. I didn't even know. So I bet it's tabbed, and there it is. This is table 2-4. So just so you're aware, there's a table 2-4 and a table 2-5. Table 2-4 is for rolled shapes like W's and like W's, channels, angles, so on and so forth. Whereas 2-5 is for just plates and bars and whatnot. The grid that we will, so let's talk a little bit about how this table is organized. So what you will see in this grid, in this table, is you'll see a series of steel grades and you'll see a series of shapes. And some of them, the squares will either be white, gray, or black. Okay? Now the black squares, what that means is, if I go to the store and I buy a W shape and I have no idea what the grade is, chances are that's the grade. That's the preferred material grade for that shape. So if you know that you're going to be using a W shape and you have no idea what grade of steel to use, go with A992 because that's the preferred material grade for W shapes. If it's gray, that means you can find that shape in that grade. If it's white, that basically means you can't. For our purposes, what I think is most important is that you understand for a given grade, how do you report the values. So if we're looking at grade A36 steel, which is a very common grade of steel for plates and for angles and whatnot. So for A36 steel, we're going to use a yield stress of 36 KSI and a tensile stress of, well, that's interesting. We have a range that says that the tensile stress can be anywhere from 58 to 80. So if you were doing a design problem, let's have a thought experiment. So if you were doing a design problem, which value do you think you should use? Say it again?
The yield.
Well, okay, so you both are kind of saying the same thing. So let me address what you were saying. Okay, so what you were saying is that between the so you're saying the minimum, but you're also saying like, well, I would just use this one. Okay, and what I'll say is that's a good instinct. Okay, but what I'll say is that, and you'll understand this next week, is that when we get into tension members, we're going to have specific limit states associated with yielding and specific limit states associated with rupture. And so we're going to need both values. But I'm saying between these, which one would you use? And you're saying, what's that? Huh?
You take the maximum or minimum?
And which one?
The maximum.
The maximum. Okay. That's a good guess, but that's not right. Okay. And let me explain why. So let's thought experiment this, okay? So I'm designing a beam that's going to support a bridge that our grandmas are going to drive over, okay? Now, let's say you assume that the maximum stress that it can hold is 80 KSI, but it's a range. Let's say you assume it's 80 and then it's actually 58. What's going to happen? Grandma's going to have a bad day. But let's invert it. Let's say you assume the worst case scenario. The worst case scenario would be you're assuming that the steel is weak, but you're assuming that the steel can only support 58 KSI. What happens if it's 80? Well, grandma's still fine. You see what I mean? So whenever there is a range, you use the minimum. Now, some of you are probably sitting there thinking to yourself, Dr. Mike, come on. Why do they even put a range? Why don't they just report the minimum? You know, why make it complicated? That's a reasonable question. That's actually an understandable question. I'll give you a short answer to give you an understanding, and I'm going to use the 1994 Northridge earthquake to sort of make the point. So the thing about steel is that when you start upping the strength, you start lowering the ductility. Okay. Now ductility becomes really, really important whenever you have extreme event loads. And a good example of an extreme event load is an earthquake. Okay. Now in 1994 there was a big old earthquake, the Northridge earthquake, and you look it up in the California area. And before then, back in like the 70s and 80s, the steel industry was strongly advocating moment frames for all of their seismic structures. So if you had a structure in a seismic region and you needed a lateral system to support the loads, you said, let's go with a moment frame. And the reason is that moment frames, and this is true, moment frames, remember how we had moment frames and brace frames? Moment frames are more ductile. And ductility is important in an earthquake, so it made sense, okay? But then after the Northridge earthquake, they started doing a bunch of, examination of buildings, and they found a bunch of fractures. And they're like, that's not supposed to happen. Wait a minute, that isn't the case. So they broke out some coupons, and they started taking those steel coupons to the lab and started testing them, and they found that these elements that were designed, assuming a 58 KSI, were actually experiencing much higher, which is fine. I mean, that's great for regular old everyday, but for seismic applications, the idea behind reporting this range is that if you ever are dealing in a situation where you need high ductility, you just kind of need to be aware that the steel grade that you're using, you might want to check that. That doesn't mean you still can't use moment frames. We still use moment frames all the time under earthquakes. We just now take that into account. That's sort of the best way I can describe it easily without getting into the weeds of earthquake engineering. So, does that make sense? Okay. One thing I will tell you is, just for housekeeping in this class, so if you notice this slide, notice how I've used the color green on the font for the manual references. So if there's ever a reference to something in the manual, like a page in the manual, a table in the manual, it will be in green, okay? So just like from a formatting perspective moving forward, I've really tried to ensure that I keep that consistent. So if there's a manual reference, it's in green. Sound good? All right. Okay, let's talk about hot rolled products. So when I say hot roll, I mean this is the steel products that we're using in this class. There is a series of products that's called cold form steel. Cold form steel is when you take, plate and then like bend it into the shape of your choosing. How many of you have ever been, I'm sure many of you have been to like a Sam's Club or a Costco or some store like that, and you look and they've got the shelves and they have like the pallets of grape jelly, you know what I'm talking about? And they have these, so they've got this big shelf and they've got these like steel little posts about like that, and they're supporting these like, pallets of maple syrup and whatnot. That's cold form steel, okay? So it's light gauge steel, but it bent in a certain way that it can support some pretty heavy loads. It's really strong stuff. It's not as strong as, like what you need for a, 200-foot long bridge, but it's a good product. We're focusing on hot rolled steel in here, and so hot rolled steel generally comes in two main fashions, like either plates or bars, and then we would take those plates and bars and fabricate them into a variety of shapes and whatnot. How many of you, I think it was, you might not have been there, but there was a tour that we had, I think it was either last year or the year before, where we toured the Nitros Bridge, the one on Interstate 64 that they just finished, you know what I'm talking about? That big old plate girder that carries traffic from exit, what is it, like 44 to 45? You know what I'm talking about? That's a plate girder. So that's not a rolled shape. They actually take plate, and weld it together to develop a customized shape. And when you have a really heavy load demand, you kind of need to do that. For buildings and whatnot, other than a few transfer girders and things like that, generally you're just using W shapes or general rolled shapes, which is what we're using. Notice how I haven't really said the word, when I'm talking about the rolled shapes, I haven't really said the word I-beam, because we don't really use quote-unquote I-beams anymore. I-beams, what I mean by that is if you open the manual, there are several different types of rolled shapes, that are I-shaped in cross-section. For example, there are W shapes, there are S shapes, M shapes, HP shapes, and they each have specific purposes. So, for example, the HP shapes are piles. So those are the shapes that you would use for foundation design. The most common rolled shape that we will use is a W shape. And it says W because W stands for wide flange. Okay. Speaking of, if we're looking at the cross-section terminology, I imagine you've seen this before, but in case you haven't and we're all on the same page, this is a flange, this is a web. Okay. And unless otherwise noted, we can assume that both flanges are going to be the same size. In plate girders on bridges, that's not the case. In fact, the default is it isn't the case. But for our purposes, unless otherwise noted, they're going to be the same size. For angles, we call the different components legs. So this leg of this angle, this is another leg. Okay? We have angles that are equal legs, and then angles that are unequal legs. Okay? Make sense? All right. All right. When it comes to naming a rolled section, we have a very specific naming terminology. Angles are the ones that are maybe a little different, but let's consider a W27 by 129. So the W corresponds to what type of shape that we're looking at. So it could be a W shape, it could be a C shape, it could be an HP shape, it could be a WT, whatever, right? So if I'm talking about a W27 by 129, the W says I'm talking about a wide flange cross-section. The 27 refers to about how deep it is. Not exactly how deep it is, but approximately how deep it is. And the reason why is that if you look at all of the W27s in the manual, there is some variability in that design depth. But that family of W27s has an approximate depth of about 27 inches. Okay? The 129 refers to how heavy it is. Okay? So a W27 by 129 is a W section that is about 27 inches deep and weighs about 129 pounds per foot. Okay? Actually, the weight is pretty exact, right? So the idea is, if I have a W27 by 129, each foot weighs 129 pounds. Okay? So for the purposes of design, remember I said that our goal is going to be selecting the lightest shape? So a lot of what we're going to be focusing on is this number. We're going to try and make sure that this number is as small as possible. Okay? Does that make sense? Okay. Angles are a little different. So like if you have an angle that's like an L 6 by 4 by a half, the 6 and the 4 corresponds to, like, if this is the angle, so this is 6 inches, that's 4 inches, and then the half is how thick it is. And I should note, this is a USCS unit class through and through. Feet, inches, kips, pounds. No kilonewtons, no meters. Okay? And it's because this is how it is, you know. So, again, I know we could have a belabored discussion about how metric probably makes more sense, but this is just what we use. So, all right, any questions? Like I said, I was planning on getting you out of here a little bit early today. I do want to show you the homework assignment just so you can kind of see what it looks like. So the homework assignment will be a quiz on Blackboard, but it's going to ask you questions like this. So it's going to say, like, for example, question 1, what is the web thickness of a W21 by 55? So which value are we going to use, the design value or the detailing value? There we go. Okay. So there's going to be a series of questions that you need to answer. Some of these are numerical, and then some of them, they're going to ask you questions about looking up certain things in the spec, so the back part of the manual. Again, I don't think this is a very difficult homework. I think it's just, I want you to open this thing, okay? But I do want to say one housekeeping item. When we come back on Wednesday, if you have your manual, bring it and start bringing it with you, because we're going to start using it pretty regularly. Sound good? I'm giving you 11 minutes of your life back. You all have a wonderful extended weekend.